Hello and welcome to the physics lab once again. Alright, so today we're here to talk about series and parallel circuits. I'm not going to get into too much about how the circuits are set up because that's, well, first of all, there'll be examples when you get to the lab so you can do them that way, or but you should also know it from class. It's not that hard. Basically what we have right here is the first one of the experimental setups we're going to measure, which is a series circuit. Now if you see here we have our power supply, a bunch of cables, I really wish I'd find those short ones, a prototyping board, the plastic thing here, and these are two resistors. This one is 100 ohms, trust me, and this one is also 100 ohms. We are also going to need a multimeter and the multimeter probes. Now today what we're going to be measuring, if we look at the Excel spreadsheet, we're going to be measuring I, which is current, and V, which is volts. So it's very important that before you start working on this lab, that not only have you watched this video, but you've also watched the video on how to measure current. I'm not going to go over that because I put that in a separate video so you can look at that for future reference. Now, what we're going to do here is we're going to turn this on, and right now I have it set to 10 volts. I think the actual voltages are in the documentation, but they don't really matter all that much, as you'll see. And then what we're going to do is we're going to start by measuring volts because volts are easier and a lot less scary. Alright, so we're going to take that, we're going to put it on, the black stays on common and the red goes to voltage. Then we're going to flip this over to DC volts and we'll put it on a 20 volt scale. The reason we're doing 20 volts is because if you look right here we have 10 volts, so approximately, so we want to stay below 20, above 10, but get as close as we can to 10. Now it asks you for the voltage across resistor 1, which is this one right here, and the voltage across resistor 2, which is this one here. So all we have to do, again, you can't blow anything up on this one, is you put your probes across the resistor. Okay? Now if you look here, we expect, wait a minute, how'd that happen? We're putting in positive 10 volts and we're getting out negative 5 volts. We're 15 volts down. What happened? Well, it's actually pretty easy. Whenever you get something like that, just flip those two around. And whoops, I dropped one. And now we're getting about 5.08 volts. So you would type in for V1 5.08. Okay? And don't round things off. If the multimeter says 5.08, you put in 5.08. Now, for V2, you'd measure the voltage across the second resistor right here. Like that. And in this case, we get 5.12. So I typed in 5.12. We'll worry about the R equivalent in just a minute. To get the V total, that's the total across both resistors, and there's actually a couple places where we can measure that. We can just go from the beginning of this resistor to the end of the last one, or we could go from this, you could use this spot for the red one, or we could even go all the way back to the power supply. Same thing with this one here, we could go back, all the way back, but we'll just leave it right where it is. And we get 10.21. So we type in 10.21. Usually it's easier to make all of the voltage measurements before you do any of the current measurements. Now I skipped one step, and that's important because I want you to not skip it when you get there. I said that the voltage wasn't important, and it isn't. What is important is the current, because in no situation do you want that current to be above 0.2 amps. And as you go along this way, and as you change the resistors out and go to parallel circuits, there are going to be cases where if you just leave the voltage at 10 volts or wherever it was, you're going to end up with currents above 0.2 amps. And then if you do that, well, you have a chance of blowing up the current meter. Now, Some people in the past, what they've tried to do now is, okay, well, I did my 100 and 100, I got all the voltages. Now I'm going to take out this one here because on the next case it says to use a 100 and a 47. I don't recommend that, just because of what I just said. If your current is messed up, or if you change the voltage or something, it's kind of hard to get back exactly where you were. So what we want to do now is we want to measure the current, and it just asks for one current on this one, not one for each resistor. Why is that? Well, because the current through a series circuit is equal for each of the resistors as in the total current. It's the same. And so remember, in a series circuit, the current's always the same. The voltage is split. In a parallel circuit, it's the opposite way. So let's measure the current, and if you remember from the current video, we take out one wire. Here it is. I'm going to put it over here. That way I know I took a wire out. I look at my power supply. I see that the current has dropped. It actually dropped all the way to 0. Now, I put my multimeter to measure current. I leave that uncommon, and I put this one all the way to the unfused. Now I took the wire out from this spot right here, so I put my current probe here and here, and I get 0.05. Is that good enough? Well, it's a good start, but it's not good enough, because then we want to go to the fused input to get a more accurate answer. And we move it over here, and we get 51.4 milliamps. So we have to know how to measure that, and that is 0.0514 amps. 51 milliamps is 0.0514. All right. So how do we determine our equivalent? Well, there's two ways to do it, and either one will get you the right answer. It's basically, it's a calculation from Ohm's law. And what we can do is either take the voltage across the whole thing and divide by the current for the whole thing. Now if I wanted to do it in Excel formulas, then I would just take the total voltage, right? And I would divide it by the current. And as you can see here, I got 198.6 amps. I'm sorry, ohms. Now, what is our theoretical? Well, in a series circuit, the theoretical is just the sum of the two. 100 ohms plus 100 ohms, which is roughly 200 ohms. So it's fairly easy. Now, you can figure out the percent difference according to that formula. Don't forget to delete it when you're done. It's right here. Right there. And then you would repeat this again, but you take out one of the 100 ohm resistors and put a 47 ohm resistor in its place. And then you do it again, and then you take out the first 100 ohm, and you'll have two 47 ohm resistors. Now, I'm not going to do that right now. It's fast, but let's not do that. So now we go on to parallel circuits. Now, the parallel circuit doesn't look like this. So we're going to have to redo the whole circuit. So we'll turn the power supply off, and I'm going to disconnect it from and I'm just going to toss it away. Well, almost. Because over here I have my parallel circuit all set up already. And don't spend too much time worrying about all this because there'll be examples in the front of the class. Now if I put this back, let's get everything off. There we go. 100 ohms there. This is a two 100 ohm resistors in parallel. Now you don't necessarily need all these wires here, but I like to use them at least at first when I'm explaining the concept. What you have here is the current comes down here through this red wire, then goes on this short red wire, supposed to be short red wire over to here, where it splits in two. Half of it, I think, let's just say half. Some of it goes, I'll put it this way, some of it goes down to this resistor and some of it goes down to that resistor. Then they come back after those resistors and they meet up again, they add back together, and then they go back into the power supply. Now, how much goes down to each one of these? Well, one way to look at this is sort of like it's a highway. And like here you have Route 101 coming south to where it splits into 12 and 101. And if you look at the traffic, let's just assume there's no other entrances or exits. The amount of cars going by the amount of traffic, if you take the amount of traffic before the split, it's going to be the same as the two after the split added together. Because we're not going to create current. Alright? Now, in the series circuit, remember the current stayed the same throughout the thing, but here the current splits. In the series circuit, on the other hand, the voltage split. So what happens to the voltage here? Well, as it turns out, it stays the same. It's a duality. So let's turn this on. And you can see already I had it set to 10 volts, and it's already pretty close to 0.2 amps. It actually is 0.2 amps. So let's turn the voltage down. Doesn't really matter where right now for our purposes today. That's good enough. Now it's at 0.16. Now, we're going to start again by measuring the voltage. So I set it up to measure voltage. And we want to measure the voltage across resistor 1. Whoops. Resistor 1. And that's about 8.27 volts. So I type in 8.27. And then I want to measure the resistance across, and the voltage across resistor 2. So I do it across here. And not surprisingly, it's almost exactly the same. I did say that it was going to be the same, didn't I? Yeah, I think I did. So I'll put in 8.26 here. Alright, now to measure the current, that gets a little bit tricky. Because we want to measure the current someplace where this circuit sees, we want to measure it before it divides up. Because if we measure it, like for example, only the current through this resistor, well, we don't want the current just through this resistor, we want the total current. Well, there's theoretically two ways we could do that. One is we could measure the current through this resistor and the current through that resistor and then add them up. Or we could just find some place before they split up and measure the current there. And there's a couple places we could do that. For example, we could do it here if we take this red wire out. We could do that. Or we could do it after they get back together and take this black wire out here, over here. Because it goes, the two come back together and then they go into this post right there. But let's do this one over here. Most people find that one easier to understand. So we take a wire out, again it's measuring current, so we have to remove a wire. Put everything else back, just the one, oh, I removed the wrong wire. Alright. So I'm trying to remove the wire that goes between those two posts, and just that wire. Hopefully I will be successful at doing that. And if you see here, I take my little wire, which should be a short one, and I throw it over there with the other one from the first part. I count the wire over there. I say, yep, there's a wire over there. It's missing. And if I look on here, my current has dropped down to 0. Why? Because I've cut it off completely. So this is good. So now I'm going, since this is the wire I removed from here to here, that's where I put my current probe. So I move the multimeter over to here, flip this over down to here, and I put my probes here and here. And I get 0.16, which is roughly the same as what it says on there. Well, that's good. So now I move it over to the fused input, over to 20, and what did I do? Oh, it fell out. Okay. I thought I broke it. And it says it's 163 milliamps. So then I type in 0.163. Very good. Now in this case, okay, we didn't measure the V-tote. We forgot to, or did we? Well, that's actually going to be the same, isn't it? So 8.27. Probably should have mentioned that earlier. No big deal. You understand, right? If you don't, let me know. All right, and then here, for our equivalent, we'll take, it's the same thing. It's Ohm's law. Our total voltage divided by our current. Well, that's going to be 8.27 divided by 0.163. And we get 50.7. Now, as it turns out, we have two 100 ohm resistors. What is the theoretical resistance according to, in parallel according to that? Well, if you don't know the formula, learn it before class, but I'll tell you right now it's going to be 50. So our hey, we got pretty good data here. I'd give myself an A with this data. All right. Yeah, I can't give myself an A. I know that. So, now we're going on to the last part. Now in the last part, we're going to measure the current through an individual resistor. Now, here I need a 100 ohm and a 47 ohm resistor. So let me turn this off for a minute. Grab a 47 ohm resistor if I can find one. You have to be very careful when you get these resistors out because as it turns out, we have boxes full of them, right? And a lot of people, when they mean to pick out a 47 ohm resistor, will pick a 470 ohm resistor, or vice versa. So be very careful, make sure that you have the right resistor. So according to this, R1 is supposed to be 100 and R2, which I've been calling the lower one closer to me, should be 47 ohms. Okay? Now if I turn this on, look at that. My current is above 0.25. So I want to turn my voltage down until it drops below 0.2 again. That's good. Alright, now if I wanted to measure the current through each of these resistors, and that's all I want to do on this one here, if I wanted to measure the current through this resistor, I have to take the part of the circuit that only goes through that resistor. So for example, if I measured the current over here on the wire that goes between these two posts, that goes to both of them. That's before the split. I have to get the current after the split, and that's this one right here. Alright? So I would have to take out this wire and measure the current going through there. Well, let's do that one real quick. I took the wire out. If you notice, my current dropped, but it didn't drop down to 0. Why? Because this part of the circuit, the 47 ohm resistor, is still there. We've only cut out one of them, one part of the circuit. So then I put my current probes in place, and let's set it up over to the unfused input again to be absolutely sure. And if you look there, I've got 0.05 amps, and now that has gone up to 0.16 because the current meter is part of the circuit. I move it over to my fused input, and I get 52.3. So that would be 0.0523. And I do the same thing with the other resistor, but I have to put my wire back in place first. So I take my current probe out, put the other wire back, and then this time I would remove this black wire here. Now, is there any reason I couldn't use, say, this black wire here, the one that goes back to where they merge back together, or for measuring this current, or this red wire over here? No, I could just as well do that. And if I was measuring the current through a series circuit, which actually I think one of these is, I just can't remember which one is which offhand. Then, for example, if I wanted to measure the current through just this resistor, then I would take out the wire, for example, that went between these posts, or the ones that went after. But as you can see, that's going to be the same anyway. So there's really no point in doing that, because this is like a highway with no exits. The traffic is always the same, unless there's somebody breaks down. So the interesting part about this whole experiment is that really it doesn't take much longer than the video that you just watched. You just watched me do almost the entire experiment. The only thing we had to do is change a couple more resistors and we would have been done. The experiment itself is pretty quick. You do have to answer these questions, and they're very simple, and actually the answers for most of it is right here in this video. So I'll see you in the physics lab.